Okay, here we begin our videos for Chapter 9. And Chapter 9 is talking about the different models of chemical bonding. Okay, so there are three main ways that elements combine. Okay, the first is ionic. Okay, when we have a metal bonded to a nonmetal. Right, and with ionic bonding, what's characteristic of that is that the electrons are transferred from the metal to the nonmetal. Okay, which is different than covalent bonding, which is our second type. Okay, and with covalent bonding, we're dealing with all nonmetals. All right, and with covalent bonding, its characteristic is that electrons are shared. Okay, as opposed to transferred, electrons are shared with covalent bonding. And our third type is metallic bonding, which is all metal. Okay, and what's characteristic of this type of bonding is that rather than sharing or transferring, electrons are pooled. Electrons move freely from one atom to another as the need arises. Whoever needs something, the electrons can move around. And this is also why metals are electrically conductive. Okay, so we're going to start our sort of diving into these types of bonding with what are called Lewis dot symbols. Okay, Lewis dots or Lewis dot symbols. Okay, and quite simply, we're going to use dots to represent valence electrons. Right, so for example, if I wanted to do a Lewis dot symbol for lithium, I'm going to use the chemical symbol for lithium. And lithium has one valence electron. Okay, so the symbol for lithium simply gets one dot. Okay, and I can put the dot, the top, the bottom, the left, the right. Doesn't really matter where the dot lives, as long as I only show one dot, because lithium has one valence. If I were to do, for example, magnesium, magnesium has two valence. So I'll write the symbol for magnesium, and I'll write two dots, one for each valence. Okay, now what's important here, and it doesn't matter where I put them, I can put them top left, top right, top bottom, left right, bottom left, bottom right, it doesn't really matter, as long as they stay separate. Okay. Let's do oxygen. So oxygen has 6 valence. Okay, so I'll write my symbol for oxygen, and I'll write 1, 2, 3, 4, and now I will start to pair them. 5, 6. Okay, and again, it doesn't matter where I have the pairs, as long as I have 2 pairs and 2 unpaired. Right now, in bonding, the reason that elements form bonds is the Octet Rule. Okay, and the Octet Rule basically says that elements will gain or lose electrons in order to get 8 electrons in their outer shell. Okay, so the octet rule is why things bond, why ions form, all kinds of reasons for various types of chemical behavior. Okay? Elements want to have at least 8 valence electrons in their outer shells. Preferably exactly 8. So let's take a look at how this plays out with ionic bonding. And we'll switch colors as we switch topics. Okay, so ionic bonding, we already talked about, is a transfer of electrons. Okay, metals tend to lose electrons, nonmetals tend to gain them. So we're going to transfer from the metal to the nonmetal. So let's take a look at an example, our good old friend sodium chloride. So if I look at the electron configurations for each, sodium's electron configuration is neon 3s1. Chlorine's electron configuration is neon 3s2 3p5. Okay, so if sodium loses that electron, it has the same configuration as a noble gas. Right now, for chlorine, on the other hand, chlorine gains 1, and has 8 in its outer shell, just like a noble gas. Okay, so if I take a look at how the Lewis dots represent this, I'll have my Lewis dot for sodium, and it has 1 valence electron. I'll have my Lewis dot for chlorine, which has 7 valence electrons. So if sodium loses 1 and chlorine gains 1, the octet rule is satisfied. So I'm going to transfer this electron from sodium to chlorine. Okay, and the result is that sodium will have a positive charge and no outer electrons to play with, and chlorine will have a negative charge and have all of the electrons to play with. Right? And so sodium and chlorine are held together by electrostatic interactions. Right? So this is how all of these ionic bonds take place. If we do another example, let's take a look at magnesium oxide. Okay, if I do the Lewis dots for magnesium and oxygen, magnesium has 2 valence, oxygen has 6 valence. Okay, oxygen needs 2, and magnesium wants to give up 2. So we get a transfer of 2 electrons. And the result is that we have magnesium 2+ with no electrons around it, and oxygen 2- with all of the electrons around it. Right? Now, in reality, electron transfer takes a lot of steps. Okay, first we have to sublimate everything so that we have gaseous elements, and then we have to atomize things so we have individual atoms, and then we have to ionize things, so we have to remove an electron, which takes energy. We have to put an electron on, which is an energy release. And all of this ends up, all these individual steps end up with a net energy deficit. Okay, so the universe has to put energy into these processes in order to make it happen. However, those processes do happen. And so what we've discovered is that there is an overall release of energy when the solid ionic compound forms. And that release of energy is the lattice energy. And the lattice energy is what results in a favorable energy balance in order for an ionic compound to form. Okay, so I'm going to go ahead and stop this video here, and we'll pick it up with an example of how we can figure out what the lattice energy is, and we can see a graphic representation of what that energy release does.